Okay, today we're going to talk about roots and rational exponents. So, first of all, what is a square root? You've probably all seen this symbol, square root. So, what is the square root of a? So, we define the square root of a formally to be some number b if b squared equals a. So, for example, one you probably know, the square root of 9. The square root of 9 is 3, and the reason it's 3 is because 3 squared is 9, or 3 times 3 is 9. So there are lots of properties of square roots and radicals and things we'll talk about. So every positive number has two square roots, one positive and one negative. So if I put the number 16 here, and I want to know what two square roots are there, well there's 4, because 4 times 4 is 16, or negative 4, because negative 4 times negative 4 is 16. Now if you see the symbol already there, square root of 16, we by convention just say that is 4. The square root of 0 is always 0, because 0 squared is 0. This symbol I kind of referred to earlier, which is a square root symbol, we also will refer to as a radical symbol. So here you see square root of 16. You could also call that radical 16. So radical 16 is 4. Just a different way to call it. Besides saying square root all the time, we shorten it to radical. The number under the radical is called the radicand. So if you see here we have the square root of 25. So you have the radical symbol, and then 25 is your radicand. The last property, for any real number c, if you square the square root, so as you can see here we're squaring the square root, you just get the radicand. So if I took the square root of 8 squared, that is 8. So let's look at some different roots we have here. Some examples. The square root of 16 is of course 4. And the reason, because 4 times 4 is 16. So then we had negative square root of 64, negative radical 64. Well, the square root of 64 is 8. And then the negative sign is on the outside, so I just put it right before the 8. Now the square root of negative 9 is interesting. This is actually not a real number. And the problem is, there is no number I multiply by itself to give negative 9. Because anytime I take the same number, say for example 3 times 3, that is positive 9. Negative 3 times negative 3 is still positive 9. So neither of those work. So there's actually no real number that multiplies by itself to give a negative number. Now that was different from this one over here, because the negative sign was on the outside of the radical. A couple more examples. Square root of 64 over 121. We can just simply think of this as the square root of 64 divided by the square root of 121, which is 8 over 11. Those are both nice roots. Okay, square root of 0.81. Now you might know the square root of 81 is 9, so the square root of 0.81 is 0.9. Oh, no square root symbol, just 0.9. So our last one, we have the square root of 12.7 squared. So as we said above, when you have this square and the square root sign, they will cancel each other out. So this is just simply 12.7. So all these roots above are what we refer to as perfect square roots. A perfect square root is just a number whose square root is a whole number. So like the square root of 49 is a perfect square root because it's 7. But the square root of 2 is not a perfect square root because the square root of 2 is some kind of decimal number. Something like 1.414. You could obviously evaluate these with a calculator, but the ones that come out nice numbers are perfect square roots and the other ones are not. So the square root of a perfect number is always a rational number. The square root of a positive rational number that's not a perfect square is an irrational number. So like this is an irrational number. It's some weird decimal like pi where it just kind of keeps repeating over and over and over again. Square root of 20 is another example because there is no number times itself that gives us 20. Okay, a different kind of root that you may have not heard of before is what's called a cubic root. So we write a cubic root with a 3 up top of the index and then a number here. So the little 3 here, it's a pretty bad 3, let me redraw that. So 3 cube root of a has a little 3 there. And that equals some b. Now that is only true if b cubed is a. So we talked about cube numbers in difference of cubes and sum of cubes. So if I have the cubic root of, say, 64, that is 4. And the reason is because 4 times 4 times 4 is 64. So here's a couple examples, and then we have the last one which has a variable in it. That's interesting. So the cubic root of 0 is still 0, because 0 times 0 times 0 is 0. Now if you look at the next one, cubic root of negative 8, this is equal to negative 2. Same reasoning, because negative 2 times negative 2 times negative 2 will equal negative 8. So interesting, on the cube roots, the inside can be negative, where the square roots it cannot. So the last one, cubic root of negative 64, is negative 4, and that's kind of the example we did up here as well. Now the variables, we're trying to think of something that multiplies by itself 3 times to give me x to the 6. Well, that is going to be x squared. And the reason is, if I take x squared times x squared times x squared, I add those exponents, which would give me x to the 6. Another way to think about it is take this exponent and divide it by the index. So 6 divided by 3 gives me my 2. Now that'll get a little trickier. If it was like 7 and it doesn't divide by 3, then we have to do something a little different to find those roots. We can actually generalize this concept for any index of any root, and we sometimes call this the nth root. So we will typically say the nth root of a number, a equals b, if b to whatever that power is equal to a. So it's the same thing, just multiple times. So here are some examples. The cubic root of 27, what times itself 3 times is 27? Well, that would be 3. Because that is just 3 times 3 times 3 is 27. So the cubic root of 27 is 3. So the same thing happens for larger order roots, such as the 4th root of 625. So if we think what number times itself 4 times could be 625, well, that number is 5, because 5 to the 4th is 625. So that's why that root is 5. The last one we have is the cubic root of x to the 6. So we're trying to think of something times itself that gives us x to the 6. So we know that that is x squared. We actually had a problem similar to this above where x squared times x squared times x squared, you add the exponents, you get x to the 6. We also said for variables, you can just divide the power by the index. So 6 divided by 3 gives us our 2. Okay, so now we're going to switch gears and go to kind of a new topic. It will look very, very different, but it actually is the same thing we have been doing all of this section. So that's what we call a rational exponent. So these are exponents that are basically fractions. So we'll start with some easy ones that typically have a numerator of 1. So if we have something, some base a, to a fractional power 1 over n. So this, for example, could be something like 4 to the 1/2, or 9 to the 1/2, or something of that nature. So what this means is that this is simply the nth root of a. So when you have a fractional exponent or rational exponent, this number in the bottom is the index of a root. So when you see fractional exponents, it actually means a root of some sorts. So 4 to the 1/2 is square root of 4, which is 2. 9 to the half is the square root of 9, which is 3. So it looks complicated with these fractional exponents, but it's really quite simple. So let's look at some examples. So we want to use radical notation to rewrite these and simplify if possible. So the first one is 25 to the 1/2 power. So that is simply the same thing as saying the square root of 25. Square root of 25 is 5. 27 to the 1/3 power is the cubic root of 27. We had this one on the previous page. Cubic root of 27, a number that multiplies by itself 3 times to give you 27, is 3. Okay, our next problem is x to the 1/5. So it's a variable to this power, so not a lot of simplifying we can do, but we can rewrite it in radical form. Since the bottom is a 5, this is a 5th root, and it's of x. So again, that little number on the bottom gives us our index of our root. And if it's blank, we of course just know it's 2, so square root. Okay, let's slide down to this problem here. Negative 27x to the 6, kind of a offshoot of what we did on our previous page. We can rewrite this one as the cubic root of negative 27x to the 6. Well, for negative 27 cube root, we know that would be negative 3, because negative 3 times negative 3 is positive 9, times another negative 3, negative 27. Then x to the 6, I feel like we've done this one a lot. This one would be x squared. And again, you can look at these indices and you can just divide them. Or like we said earlier, x squared times x squared times x squared. Add those exponents and you would get 6. Okay, let's look at some other examples where the rational exponent, where the numerator is not 1, where it's just any integer. So we have a to the m over n. So a to the m over n has 2 parts to it, but we can rewrite this as the nth root of a, just like we did before, because we can say that n is the index of the root. Index of the root, again, just means, you know, what root it is. Is it square root, cube root, whatever. But then the difference from above, we will now take our answer, nth root of a, and we will raise it to the nth power. So the top will be just like a normal power. So we will have an index of the root, and then we will also have a power, which we are raising that to. Sometimes you'll see some people put this in parentheses. That's fine. Not really necessary, but, you know, it is a nice way to go. So let's go ahead and look at some examples of this. So let's slide on down here. So we have 9 to the 3/2. So if I rewrite this, the bottom is 2. So that is a square root. And again, we don't have to put the 2 by definition. So it is the square root of 9, but then we will raise that to the third power. So we will take our root first. So the square root of 9 is 3. But now because of that 3 on the top, we will raise it to the third power. So 3 to the third is 3 times 3 times 3. So all those 3's multiplied together will give you 27. Okay, let's look at one more. So we have negative 32 to the 2/5 power. So the bottom of the fraction is a 5, so this makes it a fifth root of negative 32. But then we will raise all this to the second power. So again, there's your fifth root for the index, and there's your 2 for the power. So let's first start with the fifth root of negative 32. Now it is an odd root, so an odd root can be negative. Because you have an odd number of negative signs, you will get a negative. So negative 32, the fifth root of that is actually negative 2. You could verify that because negative 2 times negative 2 is 4. So 4 times 4 is 16, so that gets rid of 4 of my negative 2's. And then 16 times another negative 2 will give me negative 32. So negative 2, but then it's to the second power because of that squared. So negative 2 squared is 4. It is important in this case to make sure it is in parentheses because when you square a negative number, you got to make sure you're squaring that negative with it. Okay, our last type of rational exponent we're going to deal with is a negative exponent. Now, one of the exponent rules you may or may not remember from Algebra 1 deals with when you have a negative exponent. So in general, if I have a negative exponent, whatever it is, in this case it is a fraction, I always rewrite that as 1 over a, or whatever it is, to the positive power. So when I have a negative exponent, as I do in this case, it doesn't really necessarily mean anything's negative. What it does is it will flip it to the bottom. So a to the negative m over n will just equal 1 over a to the m over n. And then once you have that, the rational exponent works the same. So in this case, I could rewrite this as 1 over the nth root of a to the m, as we did on the previous page. So let's look at some examples here. So we want to use radical notation to rewrite each of these expressions and simplify if possible. So the first thing I'll do is I will rewrite this without the negative exponent. So when I rewrite it without the negative exponent, it flips to the bottom. If you did happen to have one that was on the bottom, you could flip it to the top. So now I can rewrite this in radical form. So this would be 1 over the cubic root of 27, and then that would be squared. Now the cubic root of 27, we've already talked about. That is 3, because 3 times 3 times 3 is 27. So this would be 1 over 3 squared. And then 3 squared is 9. So kind of a weird result that 27 to the negative 2/3 power is 1/9. Okay, let's look at our last example. So we have negative 256 to the negative 3/4. So we have this negative. So we can rewrite this as negative 1 over 256 to the 3/4. So now we can turn this to radical form. So this is negative 1 over the 4th root of 256 to the 3rd power. Now, negative 1 over the fourth root of 256 to the third, that would be negative 1 over 4 to the third power. And then, of course, that would 4 to the third is 64, so this is negative 1 over 64. Now, I want to try this problem again, but I want to slightly change it. Now, right now what I've done is instead of writing it like I did above, what if I were to write it like this? Well, then when I started to simplify the problem, I would first flip it, but now since the negative is inside the parentheses, I'd have to flip it too, because everything that's on the exponent would have to flip 3/4. And now if I look at it, this would be 1 over the fourth root of negative 256 to the third. But this is actually not a real number, because you cannot take an even root and get a negative number. Because if I take 4 negatives, I'll get a positive. If I take 4 positives, I'll get a positive. So there's actually no real number that this works for. So you have to be careful of parentheses. They can definitely make all the difference in your problem. Okay, so that's all our notes for section 5. When you have these all completed, you can go ahead and you can try the assignment for section 3.5.